Welcome everyone. This is CH5010 Chemical Reactor Theory. This is a postgraduate level core course on chemical reaction engineering or chemical reactor theory. Okay. So, what we are going to do in this course is basically learn tools for understanding reactions and reactors, as well as put systems and processes in context in which we can use tools for understanding reactors and reactions for various different processes. And what that is, what we are going to do and so on is what I will cover in the significant part of this lecture today. Okay, so let's do a few introductions. So my name is Niket. I am a professor of chemical engineering. I have been teaching this course for a few years now, and this is my email ID. So if you need to contact me, please write to me on nkaisare@iitm.ac.in. So if you go to the Google Drive right now, you will already see this lecture uploaded. Okay, you might actually be able to see the next few lectures also uploaded on Google Drive. So please feel free to start accessing Google Drive and Moodle. We'll use this quite extensively. So whenever you get a chance to log in, please log into Moodle as well. Again, to continue with introductions, as I said, my name is Niket. I have been a faculty in this department first from 2007 to 2011 when I was an assistant professor. Then for 3.5 years I was working in industrial R&D in Bangalore, so in General Motors and then in ABB. Thereafter, from November 2014, I have joined as a faculty again in this department. Okay. My research and teaching focus, the teaching has been on catalysis, reaction engineering, multi-scale modeling, process control. Research is primarily focused on energy systems, looking at energy as well as pollution abatement issues. So we look at energy systems, we look at CO2 capture, CO2 conversion, so catalytic conversion, thermocatalytic conversion of CO2 to fuels or value added products. We look at something called interfacial catalysis, that means catalysis happening on the interfaces. We look at control of such systems. Some of the things we also do is related to human computer interactions. So how do humans interact with automation systems and computer systems when they are operating these very complex systems. So those are the various things that we do. The group is from a research point of view well split between experimental, more about 75% of my students do experiments, about a quarter of them do simulations. So simulations will be from control optimization as well as multi-scale modeling, and experiments would be to look at metal organic frameworks, various different catalysts, zeolite catalysts, metal on metal oxide type of catalysts, carbide catalysts and so on for various transformation in broadly in energy sector. Okay. So these are my research and teaching focus. In addition to that, I'm also a coordinator at NPTEL. So several of you might have heard about NPTEL. So I'm a coordinator over there. So I look at the teaching learning platform in NPTEL. So if you have ever been an NPTEL student, the platform that you go to in order to do your assignments and so on, that a part of it was my responsibility. In addition to that, the other thing that I'm also interested is to look at teaching tools. So how can we enhance some teaching tools by using some of the more modern techniques in teaching. Okay, so those are the various things that I do professionally. Okay, so let's now start to talk about our course. The course is called Chemical Reactor Theory. Okay, so we are going to talk a lot about reactors, but we are also going to talk about reaction engineering. okay. And often in a lot of other universities, this would be a postgraduate level chemical reaction engineering course, okay. So, in this course we are interested in engineering of chemical reactions and engineering of chemical reactors, okay. So, that is really going to be very broadly what we are going to focus on. Okay. This is a postgraduate level course, okay. So, what do we mean by postgraduate is basically we are going to treat all of the concepts in a very different way than what you are used to in your undergraduate. In undergraduate, we use a bottom up approach. What that means is that we talk about the basic fundamentals, and then right in the outset we will make certain assumptions, and then we will say, for example, you would have heard about reactor called CSTR, continuous stirred tank reactor. Okay. So, in your undergraduate, probably CSTRs would be talked about very early on in the semester. So, you will take the reactor is extremely well mixed, you have inlet coming in, you have outlet going out continuously, and let us model this reactor using mass and energy balances, and then you will develop the overall balance, and then you will try to solve these balances. That is the approach that you take in an undergraduate course. We are going to follow similar but slightly different approach, and it is different in some important ways. We are not going to discuss CSTR as a CSTR, but we will discuss CSTR as a special type of reactor. So, we will look at a general overall transport equation, okay. That is what you do in transport phenomena courses. So, we will look at a transport equation, and the CSTR would be once you apply certain assumptions that are valid in the CSTR equations will come out from broadly from the transport equations. The second thing we do, for example, in undergraduate, we will take the reaction A going to B, this is the overall kinetics. We are not going to restrict ourselves to a single reaction necessarily. Okay, when we are talking about one reaction taking place in one reactor, we are basically going to discuss this as n reactions taking place where n equal to 1. Okay. So, the difference between the two is you start off in an undergraduate program, for example, describing your rate of reaction as minus RA. Okay. This is not what we are going to do. We are going to generally describe the reaction rate, okay, of jth reaction, okay, where J can go from 1 to even a million. Okay. Of course, we are not going to take examples involving million reactions, but potentially we can. The overall framework that we are going to develop will be general enough to tackle as many reactions as needed. Another example is, for example, axial dispersion was taken up as a special case of non-ideal reactors. We are not going to take axial dispersion as a special case of non-ideal reactors. Instead, we are going to talk about plug flow reactors as a special case of a general reactor under certain assumptions. So, if everything is well mixed in the transverse direction and nothing is mixed in the axial direction, that is when we get a PFR. Okay, so PFR is a special case of an axial dispersion reactor with a dispersion of 0, rather than the other way around that you had done in undergraduate. In undergraduate, we had talked about PFR first and then axial dispersion reactor. In this case, we are just going to turn the things around. Okay. People who are not chemical engineers by their undergraduate background, all of this would have felt like mumbo jumbo to you. Fair enough. Okay. We are going to start at base level. We are going to revisit all of the concepts, but we are going to revisit all the engineering concepts in the entirety. We are going to talk about the role of transport, we are going to talk about thermodynamics, we are going to talk about kinetics, and then we are going to put all of this together. So, kinetics is, for example, something that chemists amongst you would be very familiar with. Thermodynamics is again chemists, chemical engineers, mechanical engineers, people with energy background and all of that also are extremely familiar with. Transport is something that chemical engineers, but more than chemical engineers, mechanical and aerospace engineers who do transport a lot. Okay. So, this is going to be a postgraduate level course. That means we are going to have a top down approach. So, we are going to talk about these concepts, and everything that we do that is reaction engineering will be specific cases of these generalized concepts. So, we will start with general principles and then follow it up with specific treatment of those principles. Okay. So, we will view traditional CRE concepts such as CSTR, PFR, design, residence time distribution, etc., as simplifications of those broader principles. Okay. Again, what all of this means, I am sure there is a whole lot of confusion right now. We will revisit this somewhere in the middle of this course, around 6th, 7th week mark. After your midterm exam is done, we will revisit this and then we will look into these aspects. Hopefully at that time things will be clearer. Okay, so what are the prerequisites? In principle, reaction engineering, transport thermodynamics in undergraduate level may be considered as prerequisite, but that's not really true. Okay, in practice, what I really expect is you should broadly know what CSTR stands for, what PFR stands for. You need not know the equations really, but you are broadly aware of these terminologies. Okay. How many of you have heard CSTR and PFR for the first time today? Okay, couple of you. Okay. What I would request you to do is speak to your classmates, okay, and get yourself acquainted with some of these terms. Not the derivations, none of it, okay. Just be familiar with the term, okay. Again, the name BSL makes me think about an equation that looks something like this, okay. Those of you who have dealt with transport equations will immediately see that this equation is wrong, okay. This equation actually is complete nonsense, okay. But hopefully this is not the first time that you are seeing a differential operator. This is hopefully not the first time that you are seeing the nabla operator, okay. If this is the first time that you are seeing these operators, reach out to our TAs. First week is usually lean week in the semester, so this is the time when we would want to recap some of the concepts, okay. Again, you know, reasonably recap, we are again going to start with all the concepts afresh. We are not going to make major assumptions about your background because this is a class with students from various different backgrounds, okay. Aware that an undergraduate textbook has something called shrinking core model, something called Langmuir-Hinshelwood model and so on. You need not know what shrinking core is, you need not know the terminology as well, you need not know the terminology Langmuir-Hinshelwood as well, okay. Just aware that terms like this exist somewhere in the textbook, okay. That's all I expect from you with respect to background, okay. Chemical engineers would find it a little bit easier, at least in the first part of the course. Non-chemical engineers would have to put in the effort right from the beginning. But because we are going to have a more unified treatment of all of the concepts, even some of the things or the way the treatment that we are going to have in this course is going to be a little bit new to the chemical engineers here as well, okay. So, that is what I mean, you are not going to be on the same footing because for chemical engineers they have probably done 1 or 2 core courses in their undergraduate, whereas non-chemies will be doing CRE for the first time, okay. But please reach out, please seek help from each other, okay. Books and references, okay. Let me get to the blue part first. How many of you have used Fogler? Okay. These are undergraduate books, these are not postgraduate level books. These are extremely beautifully written texts, they are excellent texts, but they are undergraduate texts, which means they follow a process that is quite different from the process that we are following over here, okay. I will come to that in the due course, okay. But I get this question all the time, oh, but in Fogler there we always dealt with minus RA. Fine, it's completely up to you how do you want to deal with, as long as your answers are correct, you are going to get full credit for it. I hope that you follow a more general process of analyzing systems that we are going to do in this course, but you are absolutely free to follow any process that you think is going to work for you. Okay. For example, the whole concept of RA hinges on the definition of A as the limiting or the primary reactant in a particular reaction. Okay, but there are a lot of situations in which that particular thing doesn't hold. A very simple example is what is called as what's come up in the last 20 years called the area of microkinetic modeling, where you have hundreds and thousands of reactions involving free radical species and so on, something that physical chemists and physicists have been doing for last 50 years, which has been adopted by chemical engineers in last 20-25 years. When you talk about systems like this, those concepts that we learn in our undergraduate become very limiting. As against that, the concepts that we are going to learn in order to analyze the systems over here become more general and become more broader. Okay. Likewise, the various things that you have learned so far, pre-exponential factors, activation energy and so on, those have a physical meaning, especially when we are talking about molecular level reactions. Those have a very specific physical meaning, and they are very closely linked to the thermodynamics of reactions taking place. Okay. And you might have heard before in various different contexts that thermodynamics forms the overall constraints in which we can identify or analyze our systems. That means you can violate the kinetics, but you cannot violate the thermodynamics. If thermodynamics says something is not possible or not feasible, it is not feasible. Okay, we do not have a perpetual motion machine, we do not know of a single case where the first law of thermodynamics is violated, we do not know of a single case where the second law of thermodynamics is violated. We are not talking about nuclear reactions. In that case, the thermodynamic principle is conservation of mass and energy together, but we are restricting ourselves to chemical systems, not including nuclear reaction. That means mass balances are independently satisfied, energy balances are independently satisfied. Those form the constraints, so that they cannot be violated. So our power law models and so on, those are limited by those constraints. Sometimes in the way we do things, we don't incorporate naturally some of these thermodynamic constraints. How to do that, how to analyze systems when we also have thermodynamic constraints and so on, will not be a part of this course. Okay. However, there are courses like computational catalysis courses. For example, Professor Jitin in our department teaches a computational catalysis course, and that is the course where he deals with some of this. If I follow an undergraduate chemical reaction engineering type of a course, students at the end of this course will not be ready to understand the concepts in his course. Okay. So the aim of a course like this is to give you broad understanding, as well as to give you some of the specific tools that allow you to tackle modern and contemporary topics. Okay. For example, reaction engineering has undergone a significant change, especially in the last 17-18 years. 2007 was when Gerhard Ertl won the Nobel Prize. That was the third Nobel Prize for ammonia reaction. Okay. Here he won that Nobel Prize for showing theoretical understanding of the ammonia reaction, or of certain other principles called Sabatier principles. Again, Paul Sabatier won the Nobel Prize in I think 1907 for a different reason. But essentially what Gerhard Ertl won the Nobel Prize for was to show theoretical explanations. I'm using the word theoretical a little bit loosely over here, but essentially it was almost theoretical explanations behind what has been observed for the last 70-80 years in catalysis and in reactions in general. Okay. And the field has been especially transformed in the last 2 or 3 decades, and we need to have tools that allow us to look at this. Okay. And what's the overall range that we are talking about? We are talking about, global range where we look at, for example, pollution, ozone formation, CO2 effects and so on, right? So just a question. So typically about 2 ppm of CO2 gets added per year. How many kgs or tons of CO2 gets added per year? How many kgs of CO2 gets added so that the concentration of CO2 increases by 2 ppm? Any idea in the atmosphere? Order of magnitude, will it be 100 kgs, 100 tons, 100,000 tons, 10 power 12 kgs? What would that be? 10 power 3 is ton, 10 power 6 is megaton, 10 power 9 is gigaton. Okay, we are talking about order of magnitude 10 power 11 to 10 power 12. So that's the amount of CO2 that gets added for just that 2 ppm extra. Okay, so we are talking about really large scale problem when we're talking about abatement of CO2. Okay, at the other end of the spectrum is, for example, things that have to do with semiconductor manufacturing. What do you think is the feature size in the chips that are manufactured today? What nanometers? 3 to 4 nanometers, 3 nanometers. So today's feature size is 3 nanometers. Okay, so we need to either do lithography or we need to do deposition and so on at such precise scales. Okay, when we are talking about single atom catalysis, we are literally talking about an atom or a few atoms sitting on top of a surface acting as the catalyst. Okay, it is not just 5 atoms in the entire reactor, it is the 5 atoms in a local environment, and then that local environment you multiply it by, let us say, Avogadro's number, and that is what you are getting. But essentially you will basically have a support and let us say single atoms on this support. Okay, and this is of the order of nanometers, not tens of nanometer, a couple of nanometers. Okay, and then after this the same pattern will repeat. Okay, so that is basically single atom catalysis. So we need tools that would investigate systems at this level as well as investigate systems at a global level. Okay, and that is the reason why we are talking about the overall generalization of tools. Again, this course does not equip you to do that, but this course I hope will equip you to understand the next set of courses that you will do either at the lower end of the spectrum or at the upper end of the spectrum or at the level which connects all of those various time and length scales. Okay, so this is still a more traditional chemical reaction engineering course, but we will have the treatment in such a way that in future you will be able to deal with various different issues that one would encounter depending on the type of systems that you need to look at. For example, integration of machine learning into material analysis. Okay, again, things that we are going to do will allow you to incorporate that at the level that you want. Okay, the primary textbook that we are going to use is Froment and Bischoff. Okay, currently it is in 3rd edition, but any of those editions will be good enough. The other book that we are going to rely on a little bit is the book by Davis and Davis. The Davis and Davis book is available for download at the Caltech website. Okay, so this is the link. Again, this link will be available on our Google Drive page. So just go there, click on that link, and you will be able to get the entire PDF for Davis and Davis book. Caltech and Bob Davis has given his book free of cost for anyone who wants to download and use it. The reference books that we are going to use, Doraiswamy and Uner, it's primarily focused towards multi-phase reactors. book by Rich Maisel is focused on chemical kinetics and catalysis. So again, connecting the molecular scale with macroscopic scale. And Jacobson, that's basically a transport phenomena book which deals with transport phenomena in reacting systems. So it connects, Bird's-Stewart-Lightfoot type of concepts with, Fogler and Levenspiel type of concepts, again at a higher level, at a postgraduate level. Okay, so these are the books that we have. So some of the questions that were frequently asked when I have done taught the courses in the past, CRE in UG versus PG, I've already answered that. I don't have very strong fundamentals. What can I do? Yeah, your first couple of weeks are going to be a little light with respect to assignments and so on. So please brush up on the fundamentals, and you can very well use the undergraduate text, the Fogler text or maybe Levenspiel text, in order to get used to some of the concepts, or you can go very briefly through first 2-3 weeks of material on NPTEL, the chemical reaction engineering undergraduate courses and NPTEL, to brush up on some of the concepts. So you could definitely do that. Okay, but I'm not going to assume. I'm going to start at the basic level. I'm not going to assume a whole lot of knowledge. We will revisit all of these concepts. The treatment is at a graduate level, okay, but we are going to start afresh with all of the concepts. I'm not from chemical engineering, that's perfectly fine. We have had non-chemical engineers do quite well in the course as well. Essentially, I will ask you the question: you should be able to balance the reaction or should be able to solve this ODE. Okay, a lot of chemical engineers would be able to do both. Okay, but as long as you can do one of these two, that would be the prerequisite for this course. Okay, so that's really what is really required for a course like this. Okay, again, I will go over all of this. I won't teach you how to balance the reaction, but really short of that, everything else we are going to go over in the next four lectures or so. I'm going to go over undergraduate basics, undergraduate concepts. Okay, so what are we going to do in the next 13 and a half weeks? Okay, so it's the semester is approximately 14 weeks. Okay, so 13 weeks if you discount the exams and so on. So there are going to be basically 13 multiplied by 4. So there would be approximately 39 lectures plus 12 tutorials. Okay, so we'll have basically this split as the introduction plus say 36 to 38 lectures. We'll have 10 to 12 tutorials. Ten tutorials are planned, but we might have 1 or 2 tutorials extra based on the need. Again, you guys say that okay, let's do more tutorials, let's solve more questions. Your senior batch did that. They wanted many more questions to be solved, so I think they had 14 tutorials. If I'm 14, right? Yeah, they had 14 tutorials. We are not going 14 because then I won't be able to do anything else in that semester. But we'll keep to 10 to 12 tutorials and 36 to 38 lectures. Okay, I'm not going to rush in order to complete the syllabus. Completing the syllabus is not the intent. Okay, if we are short on time, I'm going to reduce talking about some of the concepts that I can leave them for self-study, or you can go and look at my own videos, for example. Some of the concepts which I think are more complex and more useful for your future, we will cover them in the class. Okay, so that is what we are going to do. The next thing, we are going to start with recap of CRE math and transport and thermodynamics. That's what we are going to start off with in tomorrow's lecture. We'll finish off the introduction in the first half of tomorrow's lecture and then move on to recap of undergraduate materials. And let me very quickly give you an idea of some of the research that we did 15 years back. Okay, so this is not really new research. I will talk about new research later on, but this is something, this is now reasonably well established as a field now, just to give an idea of the overall issues. So let's say you want to generate hydrogen in your chemical technology course, you would have, or in industrial chemistry course and so on, you would have studied, you know, what is done in petrochemical industry. We use a process called reforming. So what is done in reforming is you combust a fuel and then you have methane with steam heated at 700 plus degrees Celsius, and you will have CH4 plus H2O giving carbon monoxide plus hydrogen, okay, and that is used for hydrogen generation. Okay, so this was the work that we did a few years back, and that was to generate hydrogen on board, let's say, a fuel cell vehicle. Okay, at that time this was 2010, 9-10, fuel cell vehicles were being looked as one of the potential approaches for handling the global warming issues. Okay, so they needed hydrogen generation. Some of the companies like Toyota went with high pressure storage of CO2. Some of the companies wanted to investigate whether you can generate hydrogen on board a fuel cell vehicle. So the process that we used is, instead of reforming, can we use ammonia decomposition? Again, this process is becoming more and more popular once again. People are talking about storage of energy in form of ammonia, because ammonia can be more easily stored than hydrogen, and then recover hydrogen from ammonia. Why ammonia? Because NH3, as given over here, NH3 will give nitrogen plus hydrogen. There is no carbon monoxide, carbon dioxide formed in this reaction, and that is the reason for renewed interest in the last couple of years in using ammonia as a fuel for storage. Okay, so as I said, on one side there is ammonia generation. At that time we were looking at combustion in order to heat up and get hydrogen. These days we are looking at electrical heating in order to get hydrogen from ammonia. Okay. Now the overall mechanism for this reaction contained 12 reactions. Okay, and the mechanism for C3H8 combustion contained 104 reactions. Not 1, 2, 3, 4, but 104 reactions. Just to give an example for ammonia, okay, this is enumeration of all the possible reaction steps that can take place on a catalyst surface. Ammonia you might have studied in the context of Langmuir-Hinshelwood mechanism in your undergraduate if you are chemists or chemical engineers. Okay, so what happens is ammonia decomposition or ammonia formation does not take place as a single reaction. Nitrogen comes, sits on the surface, splits as N, N and N. Hydrogen comes, sits on the surface, splits as H and H. N and H will react together to give NH. NH will react with H to give NH2. NH2 will react with H to give NH3, and then NH3 will desorb. So there is adsorption, reaction, desorption steps. These are all Langmuir-Hinshelwood type of step. There might be illyridial type of steps when a gas phase molecule reacts with an adsorbed species. So if N2 plus H was going to give NH plus N, that would be an example of an illyridial step. Again, these are concepts that we are going to relook at in module number 3. So don't worry about them. This is just to give you a flavor for what type of reactions are out there after this course, not in this course. Okay. Likewise, for the 104 reactions, we have C3H8 giving C3H7 plus H on the surface. C3H7 will give C3H6. C and C bond can split. CH3 can then go to CH2, CH. Oxygen can come in and form CHO. Then it will go to CO, then it will go to CO2, OH will be formed, OH will then go to H2O and so on. Okay, with all of these complex thing, it's 104 reactions. That single mechanism containing 104 reactions can model combustion, can model reforming, steam reforming, can model partial oxidation, can model dry reforming, that is reforming with CO2, and it can even model, for example, water gas shift reaction, that same mechanism itself without any addition of any additional reaction. It can also, if it is a CH4 mechanism, it can also model the reverse step, that is methanation. That is again a reaction that is getting a lot of interest these days, especially in Europe. CO2 plus hydrogen will react to give CH4, and then you can store energy as CH4. Okay, all of these reactions can potentially be modeled with this one single 104 reaction mechanism. It does not necessarily do well for all of those reactions, but this particular mechanism can definitely model combustion, steam reforming and dry reforming reactions. Okay. So, now you have all of these complex reactions, and now we want to combine them to analyze a reactor. Okay. How we can do that is put them in different type of reactor models. The reactor models can be very complex. Computational fluid dynamics, that could be 3D or 2D reactor models. It could be 1D model with transport effect, something like your axial dispersion model. It could be something simple as plug flow model. It could be even simpler as CSTR. So, we have two CSTRs that are interacting with each other, or this could be even simpler as global energy balances. Okay. I do not want you to remember this and all that. The only reason for showing this is something that you did in process calculations course. This is something that you would have done in CRE course. If you had CRE2, this is something that you might have done in a CRE2 course, or you would do in a more advanced course, an elective and so on. For example, in our department, we have a course called Catalyst and Chemical Reaction Engineering course that Professor Krishnaya used to run. So, that is the course which dealt with this, and then you have specialized courses for computational fluid dynamics. So, why I am showing this is, in an undergraduate we necessarily followed that transition from process calculations to CRE to CRE2 and so on. We are going to look at all of this in a more unified framework starting tomorrow. Okay. That is the intent of this course, and that is what this course will cover over the next 36 to 38 lectures plus 10 to 12 tutorials. Okay. Any questions? Okay. So, if not, we will end the class over here, and we will meet again tomorrow in the same location. Okay. Thanks everyone, and see you. Bye.